The show is about to begin right now. Hello and welcome to the Weekly Space Hangout for Wednesday, March 7th, 2018. I'm Fraser Kane, publisher of Universe Today. Today, we're going to be talking about new results from Juno, a young star with a lopsided dust disk.
It's a tongue twister.
The Curiosity learns a new way to drill. And if we have time, the 50th anniversary, the 50th Falcon 9 launch this week. Joining me this week, as always, we've got Dr. Kim Cartier. Dr. Cartier, welcome.
Hey, Fraser. Happy podcast day, everyone. My favorite phrase.
As well, Dr. Morgan Renberg. Dr. Renberg.
Hey, Fraser. I was totally going to steal happy podcast day. Usually you read me first.
Beat you to it.
Ready to sneak in there, but you read my mind.
I stole it for the question show that I recorded a couple of days ago. So when the new question show drops, you'll see that I say Happy Question Show Day. And
I am so glad to hear that it's catching on like wildfire.
On. Yeah.
It really is.
Yeah.
Anytime you hear it, it's me.
It just makes me think about you.
Somebody should add that to your Wikipedia page.
I have a Wikipedia page?
I don't know. Someone should
I'm
make
scared. I am scared to see what that says.
So before we get into it, we've got an interview later on in the show. We're going to be talking to our good friend Yoav Landsman from SpaceIL. I had a great interview with him, and so that'll be showing up later on in the show. And as always, I want to remind everybody to go to the Weekly Space Hangout crew. They are, of course, this great community of people who join us every episode and chat, but also do a lot of behind-the-scenes stuff. Again, this is magic. I show up and there is in my calendar an interview with Yoav Landsman, and so we just have an interview. And I wasn't expecting that I was going to do it, and there it is. Sometimes it's someone from NASA. That's because it's the amazing executive producers in the Weekly Space Hangout crew. They're all producers, executive producers, and are able to organize and coordinate the guests that we have on the show, which is super fun. So if you want to be a part of that community, go to wshcrew.space, and they'll give you more information. All right, let's get on with this week's show. I choose, actually, Kimberly, you're on my, this is how this works. Whoever's on my screen is the person who gets to go first. Kimberly.
Minimum effort required. Thanks, Fraser.
Well, it's like, I don't want to say, oh, and now it's Morgan, and then I turn, and then it's Kimberly's face.
You're demystifying the process.
Yeah, exactly.
I thought I was just the most important person.
Yeah, usually we have to cede control to you. Tell us about a young star with a lopsided dust disk.
So Hubble imaged this really, really interesting star system with a really boring name, as always. It's HR 4796A. And this star system is super interesting because it's a very young star. It's about 8 million years old. And we've known for a while this very young star has a very bright dust disk, circumstellar disk, in orbit around the star. And we think it's such a bright and precise disk, we think there must be some sort of hidden planet in this system. And so people have been keeping a close watch on it. And just recently, Hubble imaged the system using a different camera in the infrared, and it found that the dust in this star system is way more extensive than we ever thought it was. Something like 10 or 11 times more extensive than this really compact disk that we knew was there. This is let's see what the number is. It's more than 1,600 astronomical units wide, this giant dust system, which we think formed from the collision of tiny planetesimals flinging this dust around. But this dust is not only very extensive, it's very complex and lopsided. It's sort of like smushed on one side and very extended on the other. And so there's obviously some sort of complex dynamics going on way beyond just a single planet forming.
It's amazing just to look at this image. I'll bring up the image beside you here so that people can see. Just like, this is a photograph of a dust disk around a star.
Yeah, this star, it's young, it's bright, it's doing all sorts of complex things. This is a solar system that is still very, very young and still clearly doing something that we had no idea that these things were doing. And So the so-called hidden planet, something that must have been shaping this very bright inner disk, can't be smushing this giant cloud of dust, and it's not even contained in a disk. It's this giant cloud, and this one single planet cannot be shaping this giant complex dust cloud. There has to be something else going on. Now we know that there's it's a binary star system with a tiny little red dwarf buried somewhere in there that's probably doing some of the shaping, but it almost looks like this star system has hit a bow shock in interstellar space that's compressed one side of the dust and flung it all out the back.
So
We actually have an kind of an analog in our solar system that can help us think about these kind of asymmetries in disk systems, and that's the rings of Neptune. For a long time, we thought anytime you had a big cloud of dust like this, it would tend to spread out and diffuse into kind of an even cloud. That's what happened with the rings of Jupiter, Saturn, and Uranus. But when Voyager 2 flew by Neptune, it discovered that the Neptunian rings are these short little arcs that seem to have been sustained that way for millions, tens of millions, maybe even hundreds of millions of years. And it's only in the last few years that we've started to work out that complex resonances between some of the Neptunian moons create these sort of dead zones where these ring particles collect, and then create other areas where it's very hard for ring particles to stay. And so even though it seems like these things should be spreading out, they're confined to these tight regions because of gravitational influence of objects that sometimes we can't even see. We just know must be there.
Yeah, and it's one of those things where you see all of the complex dynamics that have to be going on in this system, and you have to infer that there's something else going on there. And it's one of those interesting things, like when you or scientists think of how planets are forming in a disk, you think of this giant cloud collapsing into a star, the extra debris flattening out into a disk in a nice, neat thing, and then planets clump and generally clear everything out, and it's all very neat and tidy in fantasy land. And then you see images like this of actual planets forming, and you realize that you can't treat these forming planet systems like they're perfect isolated systems. I guess in intro physics you think of a spherical cow traveling through a vacuum, and it's so perfect. And
yeah, not all of this happens like synchronized. A planet can form and start to we often think planets form and the disk dissipates as sort of happening almost simultaneously, but it's totally possible that a planet could form and then start shaping the disk around it in that sort of intermediate time before the disk starts going away. And that could be something like what we're seeing here.
Well, how does that correspond to to our own solar system, right? Like we're seeing all of these structures. Did this happen in our own solar system at some point that would look like this?
Something like this might have happened. I mean, clearly there's a binary star in this system. There's two stars, so it's not going to be a perfect one-to-one comparison. But the scale of this dust system is certainly big enough to encompass all of the solar system, and we certainly know that there are things, out past the orbit of Neptune. It's the Oort cloud is very extensive, and so something like this very well could have happened very, very early. Though there is quite a lot of debris, and so we don't know, what planets have survived or what planets will end up forming in this kind of system. And there's just so few of these that we've seen that the more we collect, the more we try to understand. So it's possible, but there's, so many unknowns in this.
Yeah, I just want to show people again just this picture because it is just a stunning.
I mean, it's more than 1,600 astronomical units across is the image you're looking at, and it's kind of ridiculous. And you still see that super, very fine, bright ring of dust right in the center, buried within this complex cloud.
And so this is another star system far away from us, and Hubble can see this level of detail in this star system. It just blows my mind.
Yeah. For reference, that tiny little disk buried in the middle is about 80 astronomical units.
Or twice the size of the solar system.
Yeah.
The solar system up to Neptune.
So this is quite big.
Yeah. But I wonder if you can get some insights about some of the other parts, like the Kuiper Belt and maybe even the Oort cloud, these parts that are, much, much farther out from the sun than the planets and the stuff that we see. Do we get any more insights about how some of those other objects might have formed? Is it going to turn into icy material? Is it going to turn into more planetary material? As the star ages, it's going to blow that material right out of the solar system?
Well, the central star is quite a bit brighter than the sun, something like 23 times the brightness of the sun. So there's a lot of stellar radiation pressure blowing things away. And I don't know off the top of my head but the amount of scattering of light that this dust the amount of light this dust is scattering can give us sort of an idea of how big the grains are, and we might have some estimate of the density, but given all of those very vague numbers, it's very difficult to tell what will actually come of it, and we don't actually know what this material is made of yet.
And we have to apologize to the people who are listening to this as a podcast because we are sort of raving about this picture. And so
go to Hubble site. Go to the Hubble site. Do a search
for HR 4796A, and then you can see the picture as well.
It's worth reminding ourselves that we think a lot about the Oort cloud, and we say a lot of things about the Oort cloud, but we've never actually seen the Oort cloud. We've only inferred its presence. And so a picture like this is a good reminder that although we think the Oort cloud probably should be isotropic, which means that it's basically evenly distributed in all directions, it doesn't necessarily have to be. And if it was a little bit asymmetric, we probably would make the same sorts of comet observations that we're seeing today. And so until we can more directly observe some Oort cloud objects, we don't really have a good way to distinguish whether it's this isotropic scenario or this sort of asymmetric scenario that this particular star system has.
Very true.
Just amazing. All right, moving on. Morgan.
Yeah, I wanted to talk a little bit about some of these exciting new results from Juno. I think the Juno results seem like they kind of come in these bursts where it's a long time where you don't hear anything and then suddenly just a whole dump of stories. Kind of different than sort of the curiosity of the Cassini model where it seems like almost every day there was some new story. But there were sort of 3 really cool news stories that just came out this week that really hint at the kinds of discoveries that Juno is making and the sorts of things we took for granted about gas giants that now we're finding out is either right or not so right. And so all of these observations have to do with sort of the cloud structure of Jupiter, the cloud structure, and then sort of down into the interior. And one of the first observations that came out was about the depth of these bands. So if you think of Jupiter, you have these stripes, alternating kind of red and white stripes. And scientists call them bands and zones. And for the life of me, I can't remember which is the band and which is the zone. But we always assumed that they were relatively superficial features. They would extend down tens or maybe hundreds of kilometers. But some gravity measurements made by Juno reveal that they're actually incredibly deep, that these bands and zones are atmospheric features that go down 3,000 kilometers into Jupiter.
Wow, that's a lot bigger than I was ever expecting.
Yeah, and so all told, this upper sort of weather layer of Jupiter makes up about 1% of the planet's mass, compared to here on Earth, where the weather layer makes up about 1/1,000,000th of the Earth's mass. And so that, there's a lot of things that a lot of times we try to draw analogies between weather systems on Earth. We say the Great Red Spot is like a really big hurricane here on Earth, and we try to match up our atmospheric physics with Jupiter's atmospheric physics. And this is a reminder that although sometimes that works, there's a lot that's just fundamentally different about the way in which gas giants behave. And it's hard to kind of know when we're making kind of a good analogy and when we're making not such a great analogy. Another result that came out was about the rotation of Jupiter. And that's that underneath this cloud layer, 3,000 kilometers down, Jupiter rotates almost like a solid body.
Really?
And that's surprising and sort of difficult to explain. So solid bodies like pool balls or rocky planets, they're connected. So if one piece is rotating, everything else is rotating at the same rate. 1 degree a second or 365 degrees a day. But gas giants, because they're not physically connected by rigid bonds, don't rotate like that. The top rotates at a different rate than the interior. And we had always kind of assumed that there was a smoothly varying rate of rotation from the surface of a gas planet all the way down to its core. There's probably some solid rocky core deep in the middle, but all the way up from there to the surface, we assume the rotation rate was constantly a little bit different. And these gravity measurements from Jupiter say, no, that's actually not the case. It rotates almost like a solid body once you get underneath this layer. And the way they made these measurements implies that this ought to be even more true of Saturn. And
that's so weird because
like Saturn should rotate even more solidly.
I mean, astronomers will still get into a fist fight over how long is a day on Saturn.
Yeah, it's a real puzzle. And so I think this is gonna really help inform the physical models that help us try to understand the insides of gas giants. It's a really hard thing to do because the conditions there are unlike anything we can simulate in a lab and impossible to sort of directly observe. And so we need all of these constraints to try and make guesses about the physics that leads to what we see finally bubbling up to the surface.
Now, I apologize to people who are listening to this as a podcast. I'm putting up this image of Jupiter that's one that's sort of red. I guess it's an infrared from Juno. Can you sort of explain a little bit about how this sort of relates to what you've been talking about?
Yeah, so those images are of the poles of Jupiter. And this is the third really exciting story. If you remember back to the Cassini mission, Cassini revealed that the poles of Saturn had these huge, like, hexagon-shaped storms. And at that time, we'd really never seen the poles of Jupiter. And so we sort of assumed that something similar probably was going on there. But what Juno has found with its polar orbit, meaning every 2 months it passes over the North and the South Pole, is that it looks totally different. At the center of each pole is a big cyclone storm. And then on the North Pole, that's surrounded by 8 smaller cyclones. And I say smaller, but these have diameters anywhere from 4,000 to 7,000 kilometers. So that's like swallow the Earth whole size storm. And then on the South Pole, that central storm is surrounded by 5 storms. And what's really weird here is that these storms seem like they literally physically touch at their edges, but they don't combine. Like if 2 storms kind of touch on Earth, they combine into one. That's a hypothesis for why we get these hexagons on Saturn, is you have a bunch of storms forming that then kind of form one super storm that looks like a hexagon. But here on Jupiter, we're seeing, 9 storms in the north and 6 storms in the south, each one very, very distinctly separate from all the rest. And that's a real puzzle.
That's so strange. Like you said, that anytime you see a video of 2 hurricanes coming together, they always merge. And I'm just trying to imagine sort of the physics and of the cyclones that are happening, where you could have these giant masses of atmospheres that are so close and moving in such a way that they should be combining together. And I'm just trying to wrap my mind around the fact that they're so distinct. And it's just such a puzzle. Like I would expect, one would be a pentagon and one would be an octagon, and it'd be great. And we'd have all the shapes.
But the thing that we also see is we do see these smaller storms. I remember there was this one called the Oval BA, and it was the result of a couple of other mergers, and they called it like the red spot junior, and you get these storms, and they're on side by side on some of these bands, and they will merge together and form into larger storms. But these are further down on the planet.
Right. Those are sort of near the equator and not near the pole.
As opposed
These
to
are so
polar ones.
incredibly evenly spaced. The storms are all about the same size surrounding the central one. I mean, the South Polar one looks like a perfect hexagon. It just, I don't think I could draw a more accurate hexagon than that. And it's just incredible to see such regularity out of these storm systems that presumably have persisted for quite a long time, if they're anything like the Great Red Spot more near the equator.
And, I can't help but think what sort of implications all of this new information has for exoplanet atmospheres. Because like you said, we tend to take the information we have from Earth's atmosphere and weather and storms when we'd applied it to Jupiter. And now who knows if that's right or wrong. Clearly there are places where it's very, very wrong. But we do the same sorts of extrapolation for exoplanet atmospheres, where we think, oh, it has to have this sort of structure or this kind of inversion, or what if the weather circulation is like this or that, like we see on Earth? And now Jupiter, which has such a comparatively thicker atmosphere, certainly percentage-wise than Earth does, what sorts of implications does that have for these exoplanets, or some of them where we know there has to be some sort of thick hydrogen and helium envelope? And I guess we're starting to learn that we don't know all that much about them.
I wonder if there's some kind of signal that you could see in some of the data that would somehow map. Because I know that they've gotten to the point now where some of the exoplanet observations are starting to detect storms and other large-scale structures on some of these exoplanets. I wonder if you
could you think like these 9 storms that are so close together, throw them 1,000 light years away, would they not look like a single storm to you?
Mm-hmm.
And so how would we know?
Think about the 4 gas giants now. We have Jupiter has these bands and zones around its surface, and then these circular storms at the poles. Saturn has a pretty featureless surface, except at the poles where it has these hexagons. Uranus has a completely featureless surface basically everywhere. Neptune has sort of like what looks like kind of Earth-like clouds orbiting around its equator, but no visible evidence of these polar storms either. We have 4 gas giants and 4 completely different looking atmospheres. And so how can we sort of draw any conclusions about what the typical atmosphere that we should assume for a generic exoplanet might be when there's such enormous variety between them?
So you've got like the mass of the
wrong words.
You've got the mass of the planets, you've got the distance from the star, you've got the composition of the planets, the composition of their upper atmospheres, and clearly these all generate different outcomes.
Yeah, you got 2 wrong words there. There's generic exoplanet and there's atmosphere. There's nothing generic about exoplanets, and there's nothing typical about atmospheres, is what we're learning.
Yeah.
Throw them out.
So does that mean that all of the artist illustrations that we've seen are all, they're
creative liberty?
Creative liberty.
Artistic license.
I think this says you could draw literally anything for an exoplanet atmosphere, and it'd be hard to say you're totally wrong. It might not be the right exoplanet, but somewhere out there, your curlicue atmosphere is gonna be there.
That's amazing. Yeah, well, you say curlicue atmosphere, but you look at those storms on Jupiter, and it just is.
Like they look like a curlicue.
Yeah, absolutely.
I'm sure there's zigzags somewhere. I'm sure that somewhere there's a nice plaid.
figure out the atmospheric dynamics of a plaid atmosphere. I would like to.
Nice paisley. I want to see a paisley somewhere.
A paisley. Yeah.
I'm sensing an archive joke paper in here somewhere.
Yeah.
Ooh, April. April's coming up.
Is it gonna be a joke paper, or is it gonna be a
the physics of paisley atmospheres? I don't know.
That's awesome. I love it. All right, let's move on. So I'm going to talk briefly about the NASA's Curiosity rover. And of course, this has been exploring the surface of Mars since 2012. We were there for the landing. And so one of the instruments on board Curiosity, it has this robotic arm, and at the end of this arm is this drill. And what it does is it has these little clampers, and so it stabilizes when it performs this drilling operation. And so it sort of clamps onto whatever's the rock sample it's going to drill onto, and then it extends this drill between the sampling, these stabilizers, and then has a nice firm foundation to be able to pull the sample. It's done, it's gathered over the course of its journey 15 different sites and drilled this material. And it drills up this little material, analyzes it, can even bring that into its own little oven and cook it, bake it, and sort of see what kinds of gases and stuff go on. So it's got a lot of ways to do that. So the problem was back in December of 2016, the stabilizer system failed, and the drill was kind of stuck behind these stabilizers. So engineers at NASA have been working a long time. They've figured out how to get the drill out from sort of hidden behind these stabilizers, but they can't kind of retract them again. And so they can't use its original way to do this. And so then the engineers at NASA were like, well, what are we going to do? And they figured out that they can use essentially the mass of Curiosity itself to brace against this drill. And so before it sort of relied on the stabilizers on the drill itself. Now it is actually just kind of pushing itself up against where it's performing this drilling operation, and they're back at it, which is awesome.
So they MacGyvered this drill on Curiosity while sitting at JPL.
Yeah, so they ran a bunch of tests to figure out how to be able to do this, and were able to, but the hard part was to be able to actually communicate with Curiosity and convince it to be able to extend that drill permanently so that it was no longer being sort of, kept out of the way by these stabilizers. Once they were able to do that, then it's just a matter of being able to just drill. So they're kind of freehand drilling with Curiosity now.
Oh my gosh! Anyone who has ever used a freehand drill knows it's a terrible idea.
Yeah, exactly.
Don't do it if you can use a bench press.
Yeah, and this is just one example of all of the trials and tribulations that these spacecraft engineers have to go through. But I love these examples. We saw this with Kepler, how it failed so mightily, and yet it was still able to produce data. We've seen
Spirit was driving backwards for years.
Yeah, exactly. Spirit, was it Spirit or one of them was like dragging a wheel behind it?
Spirit was driving backwards, dragging one of its front wheels.
Yeah. And so originally Curiosity, now here we are 5 years later. I think its mission was, man, I remember like 90 days as well, like a very short. It was
supposed to be over ages ago.
Yeah, so it's gone.
Still doing great. And
Opportunity saw its 5,000th sunrise on the surface of Mars when it was again expected to only see 90 days. So I just love that these various missions, right? Even when they fail, even when they break down in certain ways, the mission controllers back home are able to, as you say, MacGyver a solution that keeps the science coming. And,
right, and I mean, this drill is an incredibly important part of Curiosity, right? I mean, was part of its original design goals, was to be able to take many samples and drill into the Martian surface to actually see what's there.
That's one of the things that distinguishes it from Opportunity, which has like a rock hammer basically, but not a drill.
Yeah.
So I was personally very excited to see that they were able to figure out how to still use this drill and this incredibly important part of Curiosity. It's still working, sort of. It's working, maybe not as well as before. It's still kicking around though, which is good.
Yeah, absolutely. And the last thing I just wanted to mention briefly was, we haven't had This Week in Musk for a little while. Obviously, we talked about the Falcon Heavy a couple of weeks ago.
Oh, was that a rocket of some sort?
Some kind of rocket. Something happened. Something launched. I don't really remember.
I don't remember being excited at all.
But don't make me play video of the
Please
boosters
play the
landing.
video. Please play the
But-
video. I watch that video all the time.
It's just like on an endless loop
on a
inside the
loop.
house. Just like,
On a
oh,
loop.
there it is, landing again.
Twin rocket.
Yeah,
yes.
twin rockets landing again.
That's great.
But this week, Monday night, Tuesday morning, was the 50th successful launch of the Falcon 9 rocket. So they launched this. It was a geosynchronous satellite that went off. Man,
One of the heaviest payloads they've launched.
Yeah, 30W6, I think. And so it was doing a geostationary transfer orbit, very heavy payload, so they couldn't recover the booster. And this is the thing, and I think it's really important for people to kind of see this happening, is that, you know, the Falcon Heavy, for example, when it did its wonderful return, that's in its reusable mode. But for its expendable mode, it's going to be ditching its side boosters, its core booster, its upper stage. That's all going into the atmosphere as well. You're going to get 64 tons to orbit, but all of that stuff is going to get destroyed. It's just on these lighter loads when you can actually get that full reuse. And the same thing goes with the Falcon 9. You've got these full-on geostationary transfer orbits, heavy lift, but you don't get the booster back.
It's worth realizing how much Falcon 9 use is accelerating. It took like 8 or 9 years to go from 0 to 50, but 18 of those came last year.
Yeah.
And
30 planned this year.
Yeah, the Atlas V has basically a decade on the Falcon 9, but the Falcon 9 might get to 100 launches faster than the Atlas V, even though the Atlas is at like 70 or something already. It's just the pace that they're planning to launch these things now is just ever faster. And those early days of the Falcon 9 now seem so quaint, when there'd be one or two launches in a year, and it was big news. You know, now 30 launches a year, we're not going to be able to talk about all of them. It's just going to become
well, that's
noise.
We'll see you again in another 50 launches.
Yeah. Remind me how SLS is doing again?
I think they got pushed back to 2020.
Whoa.
Sorry.
Whoa.
Sorry about that.
Oh.
It's a bunch of civil servants sobbing into their hands right now.
For all the civil servants watching, I'm sorry to tease.
Some people in the chat are also mentioning there was bad weather at the barge site that stopped the recovery. I mean, I don't know whether, I know there was like that high thrust attempt that was done a couple of weeks back, where the booster came in, and then they tried to break it right above the ocean, and then they let it sort of fall gently into the ocean, and they had to eventually sink it. But so could be that there was going to be an attempt to try and save these higher thrust boosters. All right, well, let's do our interview now. And we're back from our interview. Cool. Well, let's wrap. Did anyone think of something really clever and to talk about this week? No.
No, I did not.
Again, audience.
This week in monotony.
I want to remind you, if you can think of some really cool thing that we can talk about every week to wrap things up, that would be great. But
I could ask what your favorite kind of pie is.
Apple.
Wow, that was fast.
Yeah.
Wow, well done.
I would rather apple pie than a birthday cake. I would rather a birthday pie.
Apple pie was my first word as a baby.
Really?
Those 2 words.
And I
Overachiever.
Pedant was my third. And I don't like apple pie to this day.
Oh no!
It's one of those things that
No.
Pecan pie is the way to get to my heart.
Strawberry rhubarb.
My daughter's first word was hot, and my son's first word was dog. So, hot dog.
And there you have it, folks.
That's it. All right, Kimberly, tell us something interesting that you did this week that people should go check out.
Oh, so coming up pretty soon, you should see an article from me about a new way to figure out where deposits of ultra rare fossils might be hiding. I can't tell you more about that until it's published, but you should go check it out on eos.org in the next couple days.
Whoa. Morgan.
I have done basically nothing fun this week other than give my talk last night at a bar. I am in full-on preparation mode for next week, which is a busy week for us. I'm rolling out some new mini exhibits on the science behind machine learning, and that's been a lot of fun. But the last little push to get them onto the floor is always where you have to do all the hard stuff that you've put off for months.
Yeah. Well, I know the feeling. Dave Dickinson and I have been working like crazy to get the book, the astronomy book, completed this month. So the first draft, Dave wrote the first draft. It was wonderful. Sent it to the publisher. They had very few edits, some developmental work, so we're making our way through that. But then the bigger, or the part that I'm really working on, is bringing all the photographers together. So I've got this great community over on Instagram, and we've been selecting. It's really hard to pick which photo we want to add.
Yeah, how do you go through and choose from so many awesome
I have a list of about 5,000 astrophotographers.
Do you just get like jaded after a while? Like,
this one's great. This one's I mean, what I really want to do is I want as many of the pictures in I want as many pictures in the book to be something you've never seen, right? That's what I want. Is I want people to have never seen the vast majority of the pictures in this book. So
are these going to be like full page glossy photographs?
Yeah, it's full
that's gonna be
color.
gorgeous.
Yeah, it's going to be a great book. So this is sort of, I hope the final product will be as wonderful as everything that's going into it, and we won't know. I think the release date is in December. So anyway, I'm in the exact same camp. And in fact,
I know what I'm getting for the holidays then.
Oh yeah, absolutely. Well, we'll have me and David, on the show as guests once the book is actually out in December, I'm sure. But the other thing that we did, because I've been so busy with this, hadn't had a chance to do a full Guide to Space episode. But Paul, who's not here, and I did a talk while we were in Iceland about the limits of science, and it was quite fascinating. I got a chance to kind of grill him about that, and sort of like, did you know that there's no point making a more powerful Planck telescope? You can't find out anything else more detailed from the cosmic microwave background radiation, which is kind of
literally hit a wall.
The limits of the laws of physics. It's not how good of a telescope we can make. There's no more resolution to find out of the cosmic microwave. So anyway, check that out. We called The Limits of Science, and I published that this week. All right, let's head out. Kimberly, one last time, where do people find out more about what you're doing?
So people can always find out more by following me on Twitter, which I'm actually active on these days, at AstroKimCartier, and also check out all of my science writing at eos.org. That's eos.org.
And Morgan?
I am not active on Twitter these days, so you're better off heading to my website, morganrenberg.com. Or if you're looking for an interesting chart, find some neat facts over at chartyourworld.org.
Fantastic. All right. Thanks, everybody. We'll see you all. Oh, that's a little inception there. Okay, we'll see you all next week. And now, don't go anywhere. I'm going to run the interview with Yoav Landsman. So, Kimberly and Morgan, you're free to listen to it as a podcast.
Bye, everyone.
Listen to it as a podcast. Good night.
All right. All right, let me just get this ready. I want to go. All right, here we go. I'm going to keep tweaking this as we go. Show, and also someone who's actually working on space, Yoav Landsman. Yoav, welcome back to the Weekly Space Hangout.
Hi. It's a pleasure to be here.
But you are joining us on kind of a sad note, which is that a lot of your focus and energy, the Google Lunar XPrize, has sort of come to a stop. Maybe not for you, but for everyone else, especially Google.
I still got a job.
So just let people know kind of what happened. You know, I think we're all familiar with the Google Lunar XPrize. This is this $30 million prize put out by Google
Yeah.
for the first private group to land on the moon and hopefully have a rover or something move a certain distance across the surface of the moon. And the prize was extended, and just a couple of months ago we learned that Google wasn't going to extend the prize any longer, and the time has run out for anyone to win that money. So where does that sort of put you now?
Yeah. So first of all, the competition is not yet over. It means that the Google withdrew the prize money, but there is a chance, I guess, that the XPrize Foundation will find a way to have a new sponsor, maybe. But so the competition is still on, and we're still hoping that they will find a way to extend the competition. But we are committed to the competition. We are committed to the mission. So regardless of the results of what they will announce at the end of this month, we are doing the mission. We have a launch, and we're going to it full throttle. So it's going to happen this year.
All right, so let's talk a bit about the mission then. So this is, of course, SpaceIL. Forget it. Don't worry about the Google Prize money. You're still committed to the mission. How are things going to play out from here on out?
We're currently finishing the assembly of the spacecraft. We're testing units of the spacecraft, and when it's fully assembled, then we will start the testing of the complete spacecraft, functional tests, environmental tests. We already writing the operational procedures, and we begin the training of the crew, because the mission is very nearby. It's going to happen soon enough. So we are working very hard these days to close the last pieces of the design, the last details of the procedures design and the test design. So it's all coming together.
And what are you going to launch on?
We're going to launch on a Falcon 9 SpaceX from Florida. We are secondary payload, so it's not our launch, but with some partners, and we're going to be launched to a super GTO orbit and proceed from there.
And then if all goes well, how are you going to get to the moon?
Well, we're going to do phasing loops. It means that we're circling the Earth and gaining higher and higher apogees of the orbit with our own propellant that we carry ourselves. Actually, our spacecraft is mostly propellant by mass. It's like a tanker. And it depends. The time it will take to reach the moon is depending on where the moon will be at the time of launch, because we are not the primary payload on the rocket, we can't decide the exact date. We can suggest, but
right.
It's not promised. And also the launch can be delayed from technical reasons, as always a possibility. And it will determine if we're going to the moon and if we're going to reach the moon in a month and a half, or if it will take us several months to get there.
roughly how many orbits are we looking at? Because I remember a spacecraft that followed a very similar flight path. That was the European Space Agency's Smart 1, and it used an
Yeah,
ion engine, but did that same thing
yeah,
where
it
it
took
just
them a
kept,
year.
yeah, it took a year, right? Just kept getting higher and higher and higher on its orbit. How many orbits do you think it's going to take you to reach the moon?
It depends because the primary parameters are to leave the Earth orbit at exactly the right time. In order to reach the moon at the specific three-dimensional point in space, in order to get to the right trajectory around the moon, because we need a specific trajectory, a specific orbit around the moon that will give us a pass above our predefined landing site at a specific phase of the moon with a periselene above the landing site. So it's all coming back to the primarily maneuver that will take us there.
Right.
So the whole mission is always planned from the beginning till the end, and every change we do affects the whole mission afterwards.
But essentially, you have enough fuel if you get the worst possible launch time or
Yes.
the best possible launch time, you'll be able to make that maneuver anywhere in between.
Yes, because the number of orbits doesn't mean if we have a lot of orbits, doesn't mean we need more fuel, because the orbit doesn't consume fuel, only the trajectory corrections.
Right. Okay, and so then you get to the moon, you're going to then put yourself into orbit around the moon. How are you going to then get down to the surface, and what else happens next?
We will use the same propulsion system. We have a large thruster. It's actually a thruster that is usually used for communication satellites, for example, to push large satellites and put them in their specific slot in orbit. But we need this huge thruster in order to land, to fight the lunar gravity. So instead of pushing several tons of satellites, it will push a half a ton spacecraft. So it will be very effective. And we will use it to break the orbital velocity. And when you do that, you fall. And then you have to decrease the velocity, the vertical velocity. And we're going to sense the altitude of the spacecraft and slowly reduce the velocity until it is zero at the specific height we want it to be, where we can cut off the thrusters and take the impact from a very short, very small height.
And then your method for getting across the surface, you're not going to rove, right?
That's right. We're going to hop.
You're going to jump.
Yes, with the same thruster.
So you're going to use that same thruster that got you to the moon, that braked you
That's right.
and let you land on the moon. You're going to use that same thruster to then hop around the surface of the moon.
Exactly. With only one hop, it's enough. And while the other groups, if they're still there, they're going to roam on the surface, and it will take them some time, I guess, at least hours to do that. We're going to do it in less than 1 minute.
Right, right. And then you land, and then you're done.
And then we have to transmit the video of the movement and several other photos, and then we are done.
Right. Now, the fact that Google has decided that they're going to be removing the prize for this, I mean, have you been in contact with the other people who are working on their projects? What has been sort of the general response? Are people throwing in the towel? Are people keeping going like you are?
I wasn't in direct contact with them. I just viewed the news, anything that was published. It feels like it's not a very good situation. It makes people to think that it's not going to happen. So I'm not sure, but we might be the only group that is still on.
Yeah. So what do you think about this whole process? Because it feels like, you know, when Google set this goal out as part of the Lunar XPrize and set up what seemed like a fairly ambitious but doable timeline and a fairly reasonable goal, but again, ambitious, a bunch of groups jumped on board and were going to compete for the prize and invested. I mean, you guys have clearly invested a lot of your own money and time and so on into this. It's not necessarily you would ever make your money back from the investment that you've made, but how do you feel? Like, do you think it was should Google have just kept delaying the goal until somebody accomplished it, or does it make sense to kind of put that timeline on the end of it to wrap things up? And I know that you're going to be a little bit, you're going to be a little bit biased in your answer, but still, what do you think?
I'll try. I'll try because I think that if they I understand why they might want to cancel the competition because they delayed it several times already, but we are so close. And maybe other groups are also in close to our position and our progress. So I think it doesn't look good to shut it off at this stage. I think it's really going. I think if they ask for details, we could show them that it's going to happen.
Well, so I guess that's the question then. If you do actually accomplish the goal within a few months of when they had set it for, maybe they will release the funds.
Maybe, but I think it's an effort that the XPrize Foundation is actually doing. I hope they do. Because we don't have a direct connection to Google.
Right.
Okay, we just to the Lunar XPrize Foundation, to the XPrize Foundation. So I don't know if Google will decide to keep the competition.
Yeah, I mean, I think the thing that's really important, and this is where I have to describe my bias, which is that for a couple of years I worked with HeroX, which is an offshoot of the XPrize Foundation, and I was the product manager of the tool, that the website that people use to manage their prizes, and I deeply understand the amount of ongoing energy and effort and expense that goes to just maintain the prize itself. I mean, Google is paying the XPrize Foundation every year to keep this prize going. It's not just that Google said, "Hey, here's the prize," and then we'll just wait for the winner to show up. They're paying every month or every year fairly big checks to the XPrize Foundation to keep this prize going. And so you can see that it's not just like, hey, it doesn't matter if you just kick back and just let the prize show up when it does. Who cares? It's that they're having to make an expense every year. So I can understand why there's sort of a decision made to wrap that up, to shut that down, to not continue accumulating that expense. All right, Yoav, so just let people know when they should expect the next phase. When does your rocket hopefully launch?
The launch is for the last quarter of this year.
Okay.
So a launch date at this point is, you never have a date so far ahead.
And if the rocket does launch, how long is that transfer time going to take from when the rocket launches to when you actually perform your hop on the surface?
So it depends on exactly which date it will be. And also,
no one's going to listen to this. Don't worry. Just, some number. Is it to the nearest century?
It might be the beginning of next year, or at the end, the last days of this year.
So it'll take a couple of months from when it launches to when it actually finally reaches the moon and performs its hop.
Yes, of course. Yes.
Yeah. Okay. Great. Where can people find out more and continue to cheer you on despite the Lunar XPrize being wrapped up?
Okay, we have a Twitter account, Team SpaceIL. We have a site in English and, of course, in Hebrew, spaceil.com. And you can follow us there.
Right on. Well, Yoav, best of luck. We're rooting for you, both as a friend of the show and as one of the people who's going to continue to try to pull this off. We wish you all the best. And despite the prize or no prize, I want to see that. I want to see that hop.
Yeah. Thank you very much.
Thanks a lot.